So now we have a two-parter from Mike Flasar, his main talk of 20 minutes, and then he was asked to give a shorter 10-minute exposition on radio occultations. So Mike, are you there?
Yes, I am, but I'm having trouble seeing the presentation that Bob West just did. That's the first time that happened. So something with Zoom is uh, I can see what the view I have now with the room with the screen is enough for me because I have the talk here, but so I can tell you when to do next and all that in the current view. But yeah, it shows speaker, but it doesn't show the slides is
So
an option.
sometimes it's on your end with Zoom that if you click on the image of the room, it will displace the image of the presentation that's being shared. So that could be an
But how do
issue.
I do the other way?
Yeah,
I see the room now, which is fine
right.
because I see the talk on the screen.
Okay.
So
So
I can use that as a guide, but
all right.
I
Well,
can't see the individual slides. So if you just leave it the way it's set up now, I think it'll work because I
okay.
have also the talk on my computer.
Yep, we're going to leave it the way it is. And so you will have 15 minutes plus 5 for questions on your first talk, and then it'll be 8 plus 2. And your talks are not combined, right? They're separate?
No, they are separate.
Okay, so let's go ahead and get started. So with that, I'm pleased to present Mike Flasar, who is going to tell us about the Saturn system viewed through the infrared eyes of Cassini CIRS.
Thank you. Well, okay, next, please. Oh, you're there. Um, well, this is okay. This just shows basically shows the Sierra's team over the course of the mission. Um, we started with a handful at the time when Virgil Cundy, who was the PI, chose them. I thought, well, my God, the Sears team is basically a large fraction of the DPS, but we had to, we we added people over the years, and of course we've had some deaths too, just by nature's what they call la condition humaine. So we're not infallible or long lived. We're not gods. So anyway, that's this team. Next, please. Okay, this is um, the instrument. I've just put it on one slide because I wanted to focus on the results we've done over the years. That on the left side, the top group of slides just basically shows the instrument. You've probably had several talks on this, and also the optical remote sensing uh, palette. It used to be a scan platform, but that was descoped, and that's caused all kinds of headaches in terms of operations. Next is the conceptual layout of CIRS. It's a far infrared. Um, okay, there's a far infrared spectrometer on the left side. I guess I'm having trouble reading my. And there's a Michelson on the other side. That's a Yes, that's the on the right side is the far infrared. It's uh, uh, polarizing interferometer. That's what it is. And on the left side is a traditional Michelson, which is with a beam splitter, the kind of stuff you learn in your physics courses in high school and college. And together they cover from about usefully about 30 wave numbers. The wave number is one over the wavelength. Um, and to to 1400, which is the new 4 band of methane, or in that region. Actually, it goes to 1500. Um, The far infrared instrument is like the IRIS instrument. It's a 4.3 milliradian field of view, a single one, and then we have uh, detectors subtending a third of a milliradian each of the pixels for the mid-infrared, and that covers from about uh, 600 wave numbers or 16 microns to the new 4 band of methane near 1400 wave numbers. Um, because it's an interferometer, we can vary the spectral resolution, and the bottom panel shows that for different three different uh, resolutions. You just extend the path of the mirror and in the interferometer, and you achieve your resolution that way. And finally, there's a sample slide for Titan showing the CIRS that its highest apodized resolution uh, for Titan. Okay, next, please. Oh, okay. Now we'll talk about the Northern Storm very briefly. Next. Okay, I have to see what I'm doing. Um, I just want to point out this has been discussed before in the troposphere, but in the stratosphere, we found that a bright spot appeared in the stratosphere and persisted for nearly 2 years, much longer than the tropospheric phenomena. And this is just this just shows the appearance and the 8.6 micron figure from that Lee Fletcher provided shows that the what it looks like in an imaging type picture, but it's at 8.6 microns. Next. Oh, I have to remember to keep my okay. Um, oh, this is some detail about there were initially two bright spots that merged. We don't really understand what's really going on here, but we certainly did see it in the infrared, which you can see on the right panel here. Next. Okay. Another thing we noticed was that this is a panel showing temperatures and para-hydrogen fraction, and what we see here is that the storm was 2010, 2011, and we have before and basically after, and we notice that uh, in the in the in the in the troposphere, and basically there developed a hot region over the months after the eruption of the storm, and also you notice that the the parafraction, the amount of had been displaced vertically, and so and there was an upward motion. Now, as the Octoberg et al. Paper pointed out, well, upward motion usually means adiabatic cooling. What's going on? And so the speculation was it's like the moist convective cumulus cloud on the Earth. The upward motion is in narrow, hot towers, and in the surrounding areas, the subsidence area is a much broader area. And so the descent and the adiabatic heating is associated with the descent, and that's what's dominating which when you average over the whole thing, that's what's dominating the temperature field. Okay, move. Equatorial oscillation, one of my favorite topics. Next. Oh, thank you. Oh, this is really okay. Maybe I should just look at the screen on my computer that you've done. Okay, this is a picture of the pardon me while I try to manipulate my screen here. I'm going to actually, I can see enough of the what you see in the room just to use that as a guide. What we have seen is that the in this area is a complicated structure of temperature near at low latitudes near over several years. And what we're seeing is an evidence of an equatorial oscillation with a period, if you work it out, on the order of I believe half a Saturn a year or something like that. And so there's upward motion on the left panel, and it leads to cooling, and above you see that there's a warm region in the final panel of subsidence and heating. And basically, this is a thermally indirect circulation. It's being forced by momentum forcing, and it's just like on the Earth, analogous to the quasi-biennial oscillation and the semi-annual oscillation. Okay, so let's go to the next slide. Okay, now I'm on Titan.
And you have 5 minutes left on this talk.
Oh, this is going to be okay. Well, Juan Laura yesterday talked about the warm stratopause, and it was CIRS that actually saw that. And there's an analogous phenomenon on the Earth at the mesopause. The winter metapause is the warmest part of the Earth's atmosphere at that level. And that's kind of strange. And again, it's a case of an indirect circulation is being forced by the momentum forcing. And on the Earth, it's like gravity waves and Rossby waves. Titan has a similar kind of forcing. And what we're seeing here is basically, oh, okay. This is just showing the evolution of the atmosphere. Okay, next. And the stratospheric cross sections, we're now moving. At the beginning, was near late spring or late winter. In the beginning, when we arrived at Saturn, and it was cold at the northern hemisphere, and now you can see it shifting over starting to shift over to the opposite hemisphere. Okay, next. And the winds associated with this are similarly displayed. On the left side, it was pretty well earlier in the Cassini mission, when it was still before the northern spring equinox, and then on the left side, it's after that, later in the mission, where you actually see the winds building up in the zonal winds building up in the south. Okay. The offset pole next. Oh, I think we skipped this slide, didn't we? No, you're right. This is just showing the effects of the variation of various compounds, which I'm not going to go into because I'm running out of time. The offset pole. Okay. Well, the big surprise was the fact that the pole is not symmetric. Titan circulation should be largely symmetric because it's just such a slow rotator. But so where did this offset pole business come from? Well, it was a surprise. It turned out the way we found it was by looking at the wave number one, searching for wave number one zonal structure. And what we found is if we used an inertial system, wave numbers 1 and 2 were showing up pretty strongly. But if we went into the solar fixed system, we actually found that the waves were wave number 1. A wave number 1 is a single variation with latitude over a latitude circle over 360 degrees. Wave number 2 is two variations. That's what that. And so so we had a system in which seemed to be solar fixed structure and in a solar fixed structure with a wave number 1 behavior, and that's a sign of a tilted pole. And I won't get into details, but the next. Peter Girash had a lot of experience with Venus, and so what he initially suggested was that there was if there's upwelling, here we have a thermally direct circulation in this model. You have upwelling where the solar heating is the greatest, and that transport of angular momentum from that balances any downward transport that might be due to diffusion. And so this is a case where you have rising motion, and this is the rotation axis. The omega is the planetary rotation axis, or Venus is, of course, lying on its side relative to the Earth. And so you could get something like that. But in a case where other bodies where the maximum heating is not at the equator, but it's at some other location, with Titan, the transport might be less effective. And so there was a model here that was developed with coupling of different spherical layers on the planet by some kind of friction to balance the overturning, and they varied where the actual overturning occurred. And so this is an intermediate case, and so it's really a toy model. And so I was never completely happy about it, but it was the best we could do on that. Next. Just to know that CIRS is able to determine the methane abundance. We use the new 4 band at 7 microns, but there's also, in the far infrared, there's also several rotational lines of methane that could be used. And Emmanuel Lelouch, the Moudon crowd primarily, were able to find a variation of methane. And of course, we wondered about it, but we really can't really explain it. There was some talk that there might be some kind of infusion of methane into the stratosphere. Next. Icy satellites. Okay, I'll go through this quickly. Enceladus, we've heard about it already. It has a pole. I mean, the South Pole is hot. That was totally unexpected. Next. We actually did several observations of this, and yeah, you've probably heard this discussed already before, and you'll hear it discussed some more. But this is some of the higher, there are these warm vents actually at the South Pole. What's going on? We don't know for sure. Next. And the highest uh, uh, measurements of the South Polar region. Next. Um, Okay, we also have some weird things. Mimas has a Pac-Man. If you do the temperatures, Mimas has a Pac-Man appearance. I have Tethys here. Somehow I lost the Mimas slide in my preparation, but this illustrates it fine. It's problem. The question is, it's the question of moment of inertia. I mean, thermal inertia. Uh, that Pac-Man arises because uh, there's certain, well, as it turns out, we think it's because of the influx of high energy electrons from the from high energy electrons from, and you can see I'm in my also getting outside of my comfort zone a little bit here. High energy electrons from okay next from okay next. Oh, here we go. The high energy electrons. Okay, I have trouble reading this on the screen. Is a bombardment of high energy electrons, which actually uh, changes maybe partially melts the the ice in the surface or the particles, and it causes a thermal inertia to increase. So you could think of it as some kind of partial melting where the small particles kind of aggregate. And okay, next.
And if you could wrap it up quickly, Mike, we're at time.
Okay. Well, this is these are what Linda sent me, right? Um, Well, there's not a whole lot here. I at some point I decided I had to have something in the rings, and this is what Linda sent me. Next, and I'm not going to comment much on this. She's welcome to do that. Next, and the C ring. Okay, next, and the roll off. Right, next. Okay, this I will say, um, and people have said this. I mean, basically, Cassini was really unique. We had a diverse payload of instrumentation so that if we found something, you didn't have to rely on one instrument's capabilities to look at it. I mean, to think about it. And also, there's something like going up close when you're looking at something instead of doing it from Earth. So proximity was very important, and the longevity for Cassini was really critical. And basically, we're dealing with complex planetary systems. They're nonlinear, and they can continue to surprise us. So, and I think I'm finished, right? Yeah.
All
I
right,
think
Mike, thank you very much. And in view of the time, I'm going to suggest we go on to your brief talk about the radio occultations right now. So,
yeah, I will.
Otis, okay, so that's only a 10-minute talk, and then we'll have time for maybe one or two questions. So,
Yeah. I have to.
Is
Let me just.
yep, Cassini radio occultations.
Right, but I think I better uh find my oh no, this is okay. I'll work from this. Um the first slide is just basically what the occultation is. You measure the spacecraft is going behind an occulting body in this case, and whether it's Saturn or Titan, it doesn't matter. But and I'm only going to be talking about Saturn. I'm not going to talk about the rings because I don't. I only found out about this talk having to do it on Monday, so this is where I just put together a few slides. Basically, it's the this is really a pain. I'm sorry. No. Oh, okay. Okay, now I've got it. Um, okay, well, this is standard, and first off, let's go to the next slide. And the next slide is the occultations of Saturn's equator. We were able to, I have to, I don't, maybe it's already been mentioned, but the tour design folks led by Aaron Wolf were just fabulous because we gave them all kind of, it was a very complicated situation where we were in orbit about Saturn, but we there were demands about looking at the satellites and they had to do all kinds of maneuvers that just I'm in awe of. I just could never believe they could do this. But anyway, we managed to get a set of diametric occultations early in the mission at low latitudes and several years later. And it was basically a quarter of a Titan of a. I mentioned that there's from in a CIRS talk that there's roughly a semi-annual oscillation at the equator, and this shows it with very high spatial resolution, much better than CIRS. And what you see is that between over the quarter of a Saturnian year, that the thermal structure in the stratosphere and tropopause region changed. Now, the radiative time constant in the troposphere, pressure is greater than 100 millibars, is long, and so you aren't going to see any seasonal variations. And anyway, but now, but you see a line of activity in the tropopause region and in the stratosphere. And what we noticed was in the radio occultation is that there was a descent. Now, this is well known in terrestrial meteorology that like the quasi-biennial, like yeah, the quasi-biennial oscillation. It's a well-known phenomenon. And again, it's a question of a result of indirect forcing of the temperature field by its wave forcing. It's basically on the Earth, it's gravity waves or Rossby waves that basically dissipate, and it's momentum. It's a momentum source, and here we see it, and it was just fabulous. And so we actually were eager to get this out in GRL, uh, and I think it's one of the major conclusions from the radio science experiment. Okay, next. Here I'm just again. I mentioned that the radiative time constants are large near this in the troposphere, and what you see is also that there's from this figure of the left panel, you see that near the surface and in the troposphere, lower troposphere, the temperature variations with latitude are muted. And okay, next. But the other thing is, and again, it's the high spatial resolution of radio occultations. We saw a structure that I really couldn't pick out as easily with the CIRS instrument, which is, scale height. vertical resolution typically. But what we see here is we see this is late, almost late winter is here, and also in the high latitudes you see the as I mentioned before, the rate of time constant in the troposphere, upper troposphere and stratosphere is pretty small enough that you see large seasonal variations high up near in the lower part of the in the low, like below 50 kilometers, there's no variation at all because of the large thermal rate of time constants. And you can see that, and you can also see that there's a sharp definition toward the end of the winter season at the roughly the 100 millibar level, and actually, but it is subadiabatic, so it's stable. Okay, next. Oh, okay. This is the advantage of rate occultation. Since we're following something, we can determine pressure and altitude independently, and therefore you can't do that with CIRS because it's the nature of the rate of transfer problem. With the radio science, though, you can. And so that means you can actually ask what's going on. Now, this is the picture of the geopotential heights, the relative geopotential heights. And these are basically zonal averages, but and the dotted lines are the trajectories of the radio occultation soundings. And so this is just the geopotential heights. You use the gradient wind equation to get the winds, which is the next slide. And you see something curious here. Now you can't, because you're using the gradient wind equation, you got to be careful near the equator. So I graded it out because small errors in the blow up when you try to measure the wind. So I excluded plus or minus 5 degrees or something. I can't. But near the equator, you notice that the wind fields seem to be small. Now we know from Huygens that the Huygens probe saw a minimum at roughly the same altitude. This is about, I don't have this in heights, but it's, it's at a few tens of millibars. I used to know, I think that's like 80 kilometers or something. And that's what Huygens saw. Next.
And 2 minutes, Mike.
Okay, well, I'm nearly done. This is just with the thing blown up and showing the low zonal winds at the 20 millibar level. Next. Okay, this is my duty for the ionospheric radio occultations can sample the ionosphere too. And here's a couple papers that Arf Cleor and colleagues published on Saturn, and I'm not going to comment on these because I don't have the time and I'm not the expert anyway. And then Saturn and Titan. And I'm not going to comment on that. Maybe I'm sure there's several people in the audience that will do it, but thank you. I'm Feeney.
Right. Thank you. I'll take Chair's prerogative to ask the first question. Michael Bird promised us that you would explain why the zonal winds die down at that pressure level, which was about 60 or 80 kilometers.
Oh, Well, we gave a talk about this at the AGU in 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 I think it was 2020. I think it's what happens is that the radiative, if you look at the radiative relaxation time on Titan, um, as I said, it's very large in the lower troposphere, which is you know, there's no seasonal variation. And then in the stratosphere, there's a transition and it makes, and you see large variations in temperature. Well, but the problem is you can generate a radiative instability with this. There have been and actually I did present a model for this. And it basically involves a transfer of the instability basically transfers momentum I to the background flow, the background mean flow, and it's enough to cause a sudden damping of the flow as you move through that region. I have slides for that, but I don't have them on the screen here. But that's basically the model. And then 2020 AGU, we discussed it briefly. I haven't had time to finish this because we've been kind of between retiring and having other obligations occur. It's just on my bucket list, and I have to finish it.
Well, sounds like a really interesting model. So with that, we will thank you again for giving both those talks. Thank you, Mike.
Thank you.